So in this video, we're going to talk about what's called diagonalization. So this is section 7.3. This is officially the last bit of material that we're going to need to cover in this semester. And what we're going to do is let's first describe the process of diagonalization, what it means, how we do it, and when it's possible. And then one of the things that I was really hoping for our semester, and I was trying really hard to get slightly ahead so that I had a few days to do this, is there's an application of diagonalization that's called singular value decomposition. And singular value decomposition has a further leads to a further technique called principal component analysis. So principal component analysis. And these are things that get used quite frequently in data analysis and statistics in general. And I was hoping to have a week for us to talk about SVD and PCA, but alas, our semester has not allowed that to be possible. So what I've done is I've placed videos on these topics that are completely optional. So don't look at these videos in lieu of studying for this class or taking the final or taking any exam or whatever. But they're there. They're important enough. I want you to at least be exposed to them, the kind of main ideas. And I found a few videos that do just that. So anyway, so these ideas are there. So what we're going to do in this video is talk about the step that leads into singular value decomposition and principal component analysis, and that is what's called diagonalization. And diagonalization is, well, it's the process, and what we're going to use is eigenvalues and eigenvectors to do this, but we're going to say that A is diagonalizable if A is similar to a diagonal matrix. It might be worth pausing this video, reviewing the video on similarity at this point. Just as a reminder, A is similar to B if A is equal to P, B, P inverse for some matrix P, for some invertible matrix P. And it turns out that similar matrices have lots of characteristics that are the same. What I said in the video before is that they have the same determinant and trace, which is true, but they also have the same eigenvalues, and that is crucial for us. Similar matrices have the same eigenvalues. So a matrix A is going to be diagonalizable. So let me just say this again. A is diagonalizable if you can write A as P times D times P inverse for some diagonal matrix D. Remember that a diagonal matrix is a matrix where you have terms on the main diagonal, possibly 0, but everything else is 0. Right, so you have zeros everywhere else. Okay, so that's a diagonal matrix. And it turns out that A is similar to a diagonal matrix if and only if it's diagonalizable. So we'll actually give a nice characterization of which matrices are diagonalizable and which are not. It turns out that, I guess let's just do that now. So let's call this a theorem. It turns out that A is diagonalizable. Let me write that a little better. Diagonalizable. If and only if the sum of the dimensions of the eigenspaces, so if and only if the sum of the dimensions of the eigenspaces E lambda 1 to E lambda k is equal to n, where A is an n by n matrix with eigenvalues lambda 1, lambda 2, all the way up to lambda k. So say there's k eigenvalues. Note that k has to be less than or equal to n for reasons that we've talked about. We can have at most n eigenvalues if A is an n by n matrix. And as a corollary to this, one thing that's going to be very important for us, it turns out that if A has n distinct eigenvalues, meaning that the eigenspaces all have dimension 1, then A is diagonalizable. So then A is diagonalizable. Okay. I shouldn't have the E in there. There's a little typo there. Diagonalizable. All right. What I want to do then is let's just go through and let's talk about the different examples that we have seen already.